All right, 10 for irrational numbers. So we have not dealt with the irrational numbers before. I won't necessarily have you recreate this whole graph right here, but right there, back to one of these types of deals here. So basically what we're getting here is, natural numbers, hide and seek, 1, 2, 3, 4. Whole numbers has 0 in there too. Integers are all the whole numbers and their opposites. So -10, -9, -8, so on and so forth. Rational numbers are fractions, and decimals, positives and negatives. We've been working for a while now in this world, rational numbers. Right. So irrational numbers is what we're focusing on. They are different from other types of numbers here. They give some different, are these rational, are they not, how do you know, type of stuff like that there. So if we're going to define what they are, and there's a bit of criteria to be an irrational number. But one of the things you'll be doing right off the bat here, you'll see this type of question again, 1 through 10, classify as rational or irrational, and then why? How do you know? So we'll go through a bunch of different examples here and see what you can do with that there. Irrational numbers are numbers that cannot be expressed in fraction form. And what else do we want to say? We've got a few different things here. Rational number is expressed in decimal form. Decimal form. So you'll see decimals, you'll see fractions, kind of two things. The digits, one, they don't terminate, and they don't repeat. Which basically just means it's a decimal that just goes on forever and ever and ever without any
sort of
pattern to it, right?
Like pi.
Or specifically a repeating pattern. Yep, pi is an irrational number. Yep. So, I'll tell you the square roots that are not perfect squares. That's what we covered in 10.3, perfect squares, are irrational, always. So if it's a square root of something here, here's pi right there. If you're not, we saw that a bit last year. We'll see it again later on this chapter. You use pi when you're working with circles, spheres, ovals, cylinders, curved figures. So that's the pi symbol right there. We'll talk about, we're going to start using that a bit soon here. That's kind of about it for what we need to know about irrational numbers here. So it's just trying to understand what they are, but can't write an irrational number in fraction form per se, because a fraction is just a representation of a division problem. And if you can't get a repeating decimal or one that just ends at some point, this is the end of it here, then it's irrational. They go on forever and ever and ever here. So you can probably flip over to notes.
Cool.
There we go. Okay. So, using what we know to be true here, number 3, one for each of you there. Is it rational? Is it irrational?
Wait, so it's negative square root, or square root of negative 16, or negative square root of 16?
Where's the negative symbol lie?
Outside.
So it's asking the opposite of the square root of 16.
Oh,
Right. Inside the box is impossible. That's not rational
oh,
or
that's fine. It
irrational.
isn't even on.
Yeah, that's impossible. So that's not a real number. So that wouldn't be either rational. If it was inside the box, can't do that. All right, so number 3, Faith, what do you think?
I don't know how to do square root.
Well, you'll be behind the curve. Anybody?
I got it.
Sam?
Rational because it's a perfect square
Yeah.
four.
Perfect square. So put Faith back in the cup here. All right, number 5, 7 2/3. Colin,
Rational,
why?
because it's a normal fraction.
Right, if you can write it in fraction form, then it's rational.
Think about that
So
for a minute.
I can convert 2/3 to a decimal. It's pointless repeating. Repeating decimals are rational, but yeah, if you see it in that fraction form here, that is good. All right, 7, Eve.
Irrational?
Huh?
Irrational?
Why?
Wait, what one are we doing? 7?
So,
Mm-hmm.
Well, actually, wait, it's rational because it's a perfect square too.
No square root symbols going on in this one here. Perfect squares deal with square roots.
Well, I don't know.
Faith.
Rational because of pi?
Pi is irrational,
Yeah.
so that makes it by definition irrational. I can't divide an irrational number by 4, it's impossible. So this is irrational. Presence of pi here makes it irrational. So, Eve, number 9.
Rational?
Why?
Because it's
Anybody? Why?
It's,
It has a point.
it's rational.
Yeah, it's 0.67 as a decimal. Terminating decimals are rational. Right, just convert it to a decimal, it terminates, it makes it rational by definition. So, all right, next part here, identifying the closest perfect squares. I could kind of, I'll just make one up here. I'll say root 39. Okay, so,
W with an I, 39.
right, and what I'm doing is identifying the closest squares. Identify the closest perfect squares. So, having a foundation of what all our perfect squares are is helpful. But we know that this should be irrational. If I punch it in here, I should get some weird pattern here like that. That's neither terminating nor repeating. It just goes on forever and ever.
Do you want us to make you a coffee?
Of what?
Just a coffee.
A coffee?
Yeah.
If you really want to, I got some coffee.
Do you
here.
want cream in it?
No,
He likes
no,
it
just
dark.
yeah. I'll drink extra coffee today.
Okay.
Okay, sounds good. Thanks.
Wait, isn't that repeating? It has the 9-9.
No, it's not. It's not repeating. None of them are here. 997, 998. So may look,
okay.
but
We're gonna go 999 next.
no, who knows where it goes next there. But
990.
so clear that is an irrational. Square root of 39 is an irrational number. It's not a perfect square, but what's the perfect square that comes before root 39?
36.
Right,
Yeah, that one.
root 36, which has a value of 6. What's the one that comes after?
49.
49.
7.
Right, which has a value of 7. So then if I would say, identify the closest perfect squares, not the square roots here, this is what I would want. That root 39 lies somewhere between 6 and 7.
Why is it always 6?
So between root 36 and root 49 is where root 39 is. You're identifying the perfect square before it, perfect square that comes after it there. So not too hard to do. 51. What are the perfect squares that come before and after root 51? Somebody besides Sam.
45.
45 is not a perfect square.
Oh,
They're the two perfect squares that come before and after root 51.
well, I have the one before. I don't know
Which
about
is
49.
root 49, right? Which has a value of 7. What's the one that comes after?
So I'm trying to do that.
Eve, what do you think? What's the perfect square that comes after 51?
56.
Not a perfect square.
64.
64. Right. And there it is, right there. So all you're really doing is identifying the ones above and below. Thank you very much. Obliged. Thank you. Thank you.
Make sure there's no
Very good. That's hot coffee feeling there. Very hot. Okay. Again, I don't know what else to tell you there, so it's not real hard. You got to know your perfect squares, though. If you don't, learn them up 1 through 10 there. Be useful information to have with you here. Outside of that, what do you want me to tell you here? So, calculate table of square roots. Estimate the irrational numbers to the nearest tenth. So, it's certainly not uncommon to deal with irrational numbers in the math world here. Sometimes you can leave them in a certain form here. We're not really going to get into that here at St. Francis. You can learn more about that in high school. But for things like finding measurements, area, I mean, you need to be able to convert these different things. There's different types of formulas. We're going to get introduced to one tomorrow with the Pythagorean theorem.
Yeah, that's terrible.
That can lead to irrational number type answers, where your final answer of the missing measurement is like the root of 111. Well, how do I write that as a measurement and stuff like that? So as we go ahead into future lessons here, most of the directions are going to identify to ask us to round answers to different place values. And they'll shift around between the 10th and the 100th column and stuff. So that gives us, it's not the exact number per se, but I mean, if I have to write down what this is as a measurement here, rounded to the nearest tenth, well, I'd probably say it's 6 2/10 feet. I'd just round down to the nearest tenth. Or if I went to the hundredths, 6 24 hundredths per se. And that way we have a number. That way we can punch those into calculators. We can do more calculations. We can find out other things here. So in the math world here, you just have to be able to convert or have a point of where you take your irrational numbers and then classify them somewhere, just like pi. I mean, I got a pi button right here. There it is. There's pi. But it's much more common to just say pi is 3.14. You guys know. It's got its whole day. Pi Day. Mrs. Melcher likes Pi Day a lot. She bakes
loves Pi
pies and stuff, so for the high school. To
She
me,
bakes
it's just
pies?
another day, but on Pi Day, oh yeah, she gets into Pi Day quite a bit. She has a
She
song
makes
for Pi
pies and
Day.
brings it to school.
Right, she has a song she sings for Pi Day. And there's Mole Day too, MOL. It's another type of measurement there. That's another big day in her life.
Did she
so
bring in
Mole
molds?
Day there.
Did she bring in molds?
You'll see that when you get into physics there, what the mole is. So, MOL, you can research it on your own. There. What it is there, it has its own day too, Mole Day. MOL. Not MOLE, one that goes in the ground or that's on your
So what
face,
did you
but
do for that day? Mold day.
she sings songs again and things like that.
She make them do any work on mold day?
Yeah, they work with the moles. So, but anyway, this is just again an example of a commonly known irrational number. But frequently, when we're doing math, you got to be able to punch it in here, and this is how you would do it here. We just call it 3.14. Is it exactly exact? It is not, but is it generally close enough for the purposes that you need when dealing with circles? Usually. And everything you'll do through high school, it'll be good enough for you. So, but yeah, again, you can go back to precision. I mean, how precise do you need a measurement to be type of stuff here? How far do you need to take it out? I mean, if you're digging a deck and, I don't know, you probably want to be probably to the meter, maybe the 10th here. If you're dealing with, I don't know, parts for a nuclear reactor, you may take it out a few more decimals than if just a piece of lumber you're putting on your deck here. So depending what the application is of whatever it is you're doing, specific fields, how far you go with different values and irrational numbers can matter, but I mean through high school here it'll just say round to this, round to that type of stuff here. So for this here, number 16, I'll just do a couple, but if I say number 3, the square root, I just go to my calculator, push the 3, push the square root button. If I round that to the nearest tenth, 1 7/10, right, that's what I'd put there. What's the square root of 4? 2. And then 5, go to 5, push it in, round into the nearest tenth. The square root of 5 is 2 2/10, 2.2. So, just fill in the table up through 20 there. Really shouldn't, one square root, you should know 1, 4, 9, and 16, I would think off the top of your head, hopefully, but the other's not a hard exercise here, but you'll see a lot of different irrational numbers, and again, name of the game is trying to turn them into a rational number, rounded, approximate rational number, because I can do something with 2 2/10 here. If I need to figure something out, I can multiply it by 65 or whatever I got to do here. So, but this number as is here, I mean, if I take the square root of 5, then I get, what are we doing here? 5 square root. Oh, 5 square root. There we go. Multiply that times 65. Well, I'm still dealing with a bunch of random numbers here. So, does that make sense why we do that there? Okay. This is all setting up, by the way, this lesson for tomorrow's lesson, the Pythagorean theorem here, which takes a little bit of work. We'll be using our knowledge of squares, square roots, how to undo those things. We'll be using our algebra skills to find missing side lengths of triangles, the A, the B, or the C side there, of right triangles specifically. So you'll get to see how some of this stuff all comes together here in a real world math context, and that we can solve for
It's the sideways, it's the
long
left-
side.
Yeah.
opposite the right angle. It's opposite the right angle. We'll cover it tomorrow in a bit more depth.
I
So
don't like that. Tomorrow's lesson was not.
it's all Pythagorean theorem always deals with right triangles. The hypotenuse is always opposite the right angle. It's always the longest side too. So, but it'll be our first opportunity to kind of apply some of this knowledge with irrational numbers, squares, square roots, algebra, put it all together and find some useful information, such as measurements. People in the real world will use Pythagorean theorem to find missing measurements of things that help them. Anybody that does any carpentry or framing or construction, I mean, this is something you'll want to do, so, and do. Truth be told.
You still do that as a store fruit hall.
Right.
Well, I know.
So again, this shouldn't be a terribly hard lesson here. Trying to learn your perfect squares up to 1 through 10 would be helpful, so that you just have that information filed away here. And then answering these here about the rules that we talked about here. We'll go through each one of them, but make sure you're ready to prove your point. Otherwise, it just feels like a 50-50 yes if you just say, it's rational. Right? If I go, why? And then you go, I don't know. Well, then it's kind of like you just guessed at it. You didn't really prove anything to me here. So be ready to justify your work here with these. I can't really think of much else. So, anything else? All right. Why don't you guys should work on your 3, if we got time here, maybe in 10-15 minutes, let's check it. So get 10-3 done.